All right. So for Unit 10, we start talking about carbohydrates, and carbohydrates deal with structural isomerism, right? And we've seen isomers before, right? Isomers are structural isomers, where we have the same chemical formula. So each one of these here, right? Each one of these here happens to be C4H10. So we have C4H10, C4H10, but you can see that the structure is different, right? So the structure is different here, and this is what we deal with um, when we're talking with carbohydrates. All right, so different types of isomers that we're now going to come across. So we understand what structural isomers are. And now we're going to talk about what we're going to call stereoisomers. So stereoisomers are what we consider non-superimposable images, is that they look almost identical, uh, but you cannot superimpose them. So what I mean by superimposing is just kind of a little demo. Is this your if you take your left hand and you face it downward, and then you take your right hand and you also face it downward. When we talk about superimposing, is that I'm going to take my right hand and I'm going to directly place it over my left hand. So if you're doing that, you notice that 4 of your fingers line up, but your thumbs do not line up. And these are what we consider non-superimposable mirror images. If you were to stand in front of a mirror and you put your right hand towards that mirror, it looks like your left hand. If you put your left hand up in the mirror, it looks like your right hand, and they look identical. But you cannot superimpose mirror images that are stereoisomers. So stereoisomers cannot be superimposed, even though they look identical to another molecule. So when we have these stereoisomers that are not superimposable, we consider those, what we call those enantiomers. Right. So any organic molecule that contains a carbon, and we're going to consider this one in the center to be carbon here. As long as I have 4 different groups attached, we have this pattern here. We notice this pattern here. It doesn't really matter what the element is. If we're just looking at this pattern that's on each one of these, you notice that they're all different, which means that this carbon is chiral. And now if we use an element here, so if I put carbon in the middle, I'll put fluorine, chlorine, bromine, and hydrogen around that. And you can see that there's 4 different, and I'm not going to say elements. What I'm going to say is I'm going to say there's 4 different things attached to it, right? So it's really, I'm going to really kind of hone in on that. There's 4 different things here. We have a fluorine, hydrogen, bromine, chlorine, and because they're all different and they're all attached to this carbon is chiral because I've got 4 different things attached to it. So here, let me draw another molecule, hydrogen, bromine, we'll put chlorine over here, and then let's put another hydrogen on there. Well, now we only have 3 different things. The hydrogens are both the same. Then we have chlorine, and then we have bromine over here. So because of that, we only have 3 different things. which makes this carbon, this is what we're going to call a chiral. And a chiral just simply means that it's not chiral, right? So we know we have a kind of an understanding now of what is a chiral carbon and what an achiral carbon is. So as far as enantiomers go, we deal with mirror images. So here we have hydrogen, bromine, chlorine, and fluorine. And let's say this is my mirror plane right here, and I want the reflection of this. So this is kind of me putting my left hand up, and then I'm going to draw what seems to be my right hand. Bromine here. Cl. So what it seems to be is that, so we do have a mirror image, but we don't have any dimensionality involved in these structures here. So what we're going to use, and we talked about this in organic chemistry, is that I'm going to reintroduce these dash wedges, these darkened wedges, and these straight lines here. So I'm just going to make some adjustments here. So we're going to use this dashed wedge here. I'm sorry, this darkened wedge here. I'm going to change this to a dashed wedge. And then over here, we'll do the same. I'm going to go with a dashed wedge. And then we have this darkened wedge where the bromine was at. All right, so now what we have here is these are mirror images. These are non-superimposable. And we have chiral carbons. So these stereoisomers here are enantiomers. So those are going to be what we're going to consider these. So they are stereoisomers and what makes them a stereoisomer is that they both contain this chiral carbon, right? They both contain the chiral carbon, and because I have a pair of those and because they're non-superimposable, we're going to consider those enantiomers. All right, so let's take a look here. So our rule, and again, our rule is 4 different things. So before we move on to these examples here, I'm just going to draw another structure here. Let me use expanded structural formula. All right, so here I have a structure. And we're going to go carbon by carbon. We're going to decide which carbon is chiral and which one is achiral. So if I start here, well, let's take a look. I have hydrogen, hydrogen, hydrogen. And our rule for chirality is 4 different things. 4 different things. So we have 3 hydrogens that are all the same. So obviously that is not going to be a chiral carbon. Well, let's go on to the next one. Well, I notice already that I have hydrogen, and they're both the same. So that is not going to be a chiral carbon. So here, this is achiral. And this one is also achiral. And this one is also going to be achiral because we see the 3 different hydrogens around there. All right. So now we need to, so we know which ones are chiral, but there is one carbon that we just haven't taken a look at yet. So this carbon here, I'm going to circle the 3 different things, right? So when we look at these, here's one thing. I have fluorine. And here is another thing, and that's going to be my chlorine. Now, when I really stress this, I don't look at the elements, because if I only looked at elements, well, I have carbon and I have carbon, and those are the same. But that's not how we look at it when we're looking at chirality, is that we look at this entire thing is attached to that carbon. This thing here is attached to this carbon, and that thing has a name, and that's a methyl group. And then if I take a look over here, I'm going to look at all of this. That entire thing, that ethyl, is attached to this carbon. So I have ethyl, methyl, fluorine, chlorine, all attached to that carbon, and this carbon is chiral because I have 4 different things attached to it. So let's take a look at these other examples here. So here's 1, 2, 3, but these are the same. So this is going to be achiral. I have 1 thing attached, 2 things attached, and I only have 3 things. So again, this now is going to be achiral because I only have 3 different things attached to it. Here, just similar to my example that I just had here, well, here's 1 thing, 2, 3, 4 different things that this carbon is, or this molecule here is chiral. And then if we look at this bottom structure, okay, well, let's take a look at this one. So here, these are all the same here. So this is not going, that carbon is not going to be chiral. That's going to be achiral. The next one here, I have 1. And let me clean this up a bit before we do that one here. I think we can already knock this one off over here because I have 1, 2. And when I say the thing, I'm looking at this. So I got 3 different things attached to it. So that carbon is not going to be chiral. So let's look at that middle one. So let's take a look at this carbon here, and I'm going to circle all the things that are attached to that carbon. So here's 1 thing, hydrogen. Here's a hydroxy. There's this methyl group attached to it. And then I have a carboxylic acid functional group attached to it. So I definitely have 4 different things that this is chiral. All right, so it is also plausible, and it'll happen quite often, is that some of these molecules will have more than 1 chiral carbon. So more than 1 chiral carbon. So let's see what that looks like. All right, so now I've drawn this molecule, and this is a carbohydrate here. So this sugar, this carbohydrate here, let's take a look at this. So we're going to look at this from several vantage points here. So I'm going to redraw it a couple of times, and I'm going to draw the same molecule over again so that we can see each carbon. And I'll draw it one last time. Actually, with this one, you know what I'll do with this one here? Because it's an aldehyde, I'm just going to do this. I'll do CHO. That way it gives us a little bit something different to look at, but will mean the same thing. All right, so let's take a look at this first one on the left here. So we already know that this carbon here is achiral because I only have three things attached to it. I have this oxygen, this hydrogen, and then I have this entire thing here that's also attached to it. So I already know that is not going to be a chiral carbon. And that's going to go for all of them. So we know that this one is going to be achiral. And because I know it's an aldehyde, it's got a double bond there, it's got a carbonyl, and I already know that that's going to be achiral. All right, so let's take a look at this next one here. So this carbon here, and I'm going to circle everything that's attached to it, everything attached to it. So I have this thing that's attached, this thing, and then I have this thing. So is that a chiral carbon? Yes, that carbon is chiral. And now I'm going to go to the next one. So now we're taking a look at this carbon here. And here I have this thing. Good morning, sweetie. Mwah. I'll say hi to everybody. Say hi.
Hi.
Say good morning.
Good morning.
All right, so there we have that thing there, this thing, and then we have this thing. So again, we have another chiral carbon. Let's go to the next one. I'm going to circle everything that's attached. I have this thing, and I have this thing. So those are going to be my three chiral carbons. Once I get down here and I see both of those hydrogens there, then I already know that that's not going to be chiral because two of them are identical, right? But the ones that are asterisked here, other than this one, the ones that have asterisks, those are going to be our chiral carbons. So we can definitely have more than one chiral carbon on a molecule. All right, so let's see. Do we have another? So let's practice here when we're looking at this. So this first one here, the first carbon, number one. I'll just number these here. 1, 2, 3, 4, 5, and 6. Carbons number 1 and carbons number 6, I already know are going to be achiral. 1, because it's an aldehyde, and I'm only going to get 3 groups because of the carbonyl. Number 6, because I notice 2 hydrogens there, so I already know that that's going to be achiral. So now I kind of have to check the rest of them. So here, for carbon number 2, let me do this in a way that I can erase really well. So for carbon number 2, I have this thing. I have my hydrogen, hydroxy, and then I have this entire thing attached to it. So carbon number 2, definitely chiral. Carbon number 3, I have the hydroxy, the hydrogen, I have this, and I have this. So again, number 3, definitely chiral. Number 4, I have this thing, this thing, uh, this thing up here, this thing down here, and we can see that, yep, that carbon is definitely going to be chiral. So carbons number 2, 3, and 4. Oh, and then, you know, carbon number 5 is even. We skipped one here, one of these carbons. So carbon number 5, here's 1, 2, 3, and 4 different things attached to that. So carbons number 2, 3, 4, and 5 are going to be chiral. And you're going to see something similar to this one here. So I think we can, you know, identify these rather easily now and take a look at this. This is going to be chiral, this is going to be chiral, this is chiral, this is chiral. And I can now kind of easily identify all of my chiral carbons a little bit faster now when we're looking at these. This one here is slightly different, but we can definitely figure it out. So if we start with, let me number these, 1, 2, 3, 4, 5, 6. So as soon as I see the CH2, I know that that's not going to be chiral. So that is not, carbon number 1 is going to be achiral. And anything with a carbonyl, well, that's also going to be achiral because I'm not going to be able to get my 4 different things on there. So carbon number 2 is also going to be achiral. And then I could take a look at number 6 and I see the CH2. And again, I know that, so I got 1, 2, and 6, I know for sure are achiral. All right, so let's take a look at the rest of them here. So if I take a look at, I can identify this as being chiral, chiral, and chiral simply by just looking at them now. So we have 1, 2, and 6 that are achiral, and we have 3, 4, and 5 that are chiral. All right. And if you guys do have any questions, you know, make sure that that you are asking. Pull up the chat real quick. Yeah, feel free to stop me if you guys have any questions at all. All right. So using these dashes and wedges, right? So we've talked about these. So this dash here, just as a reminder, this dash means that the hydroxy group is coming towards you. And if we use a dashed wedge, that means it's going away from you. So Emil Fischer kind of looked at these carbohydrates, these molecules differently. And just like we make some assumptions that if I draw this structure here, from organic chemistry, we assume a few things. We make some assumptions. I assume that this has 4 carbons. Even though I don't see the letter C there, I make an assumption that there's 4 carbons. I also assume that at this location, there's 2 hydrogens, and I assume at the very end, there's 3 hydrogens. So these are assumptions that we make. So now we're going to make some new assumptions regarding these dashes and wedges. And looking at our Fischer projection. So anytime that we see this horizontal line, whatever's on the ends of those are going to be going towards you. Anything on a vertical line means that whatever elements are there are going away from you. So here, if I want to know which elements are coming towards me, well, it's any element that's on a horizontal line. So here, hydroxy, hydrogen, 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 hydrogen. So all of these are going to be kind of pointing towards you in the structure. And ones that are going away from you, so here, if it's going away from you, this would be going away from you. This would be going away from you. So now we can kind of get some 3D dimension from a two-dimensional drawing. So we know what's going towards us and we know what's going away from us. So these are going to be what we're going to call Fischer projections here. So this particular sugar here that has 1, 2, 3, 5, 6 carbons. One last thing here before I forget and move on. Anytime that we have this crosshair, this section here, this intersection means that there's a carbon located at each one of those intersections, right? So here we see carbon number 1, 2, 3, 4, 5, and then this one's clearly labeled out as carbon number 6. So that's how we're going to identify how many carbons we have in these sugars. So this particular sugar is what we kind of call an aldose sugar. So it belongs to the family of what we call aldoses because this particular sugar has an aldehyde functional group. And here is our aldehyde functional group, right? That carbonyl, that double bonded carbon with the hydrogen there, that is our aldehyde functional group. So because there it's an aldehyde, it belongs to the family of aldoses. So just kind of a drawing here, what just kind of going over what we just so we saw these horizontal lines, right? And that means that it's going towards you, and that's why we see these darkened wedges here, right? Because that represents something that's going towards you, right? So we tend not to use this structure when we're drawing Fischer projections. So when we're drawing a Fischer projection, we're literally just drawing these bare bones structures here um, that represent. All right, my mic got turned off. Can you guys still hear me?
Yes.
Okay. So this is what we're going to consider a Fischer projection here, right? Uh, So this is our Fischer projection. It's this bare bone structure with horizontal and vertical lines there. Another family, so we've already talked about aldoses, right? Another family that we're going to have is what we're going to call a ketose, right? Ketoses have a ketone functional group, right? This is our ketone functional group. All right, and we can see that here. Here's our double bonded oxygen. Here's our carbonyl. This is going to be an R group, and here's another R group. right? So it does represent this ketone functional group. So I'm not going to have you memorize a bunch of structures like this, but there are going to be parts of these sugars, these carbohydrates, that I do want you to know, right? Is that you have to be able to recognize this aldehyde functional group, and you have to be able to recognize this ketone functional group so that you can identify ketose and you can identify an aldose. Uh, Now, as far as naming these, so we can identify an aldose and we can identify a ketose very, very easily. So if I draw two structures here, right? You should be able to identify that, oh, there's my aldehyde, that this is an aldose. You should be able to recognize, oh, there's my carbonyl. There's no hydrogen attached to it, that this is a ketose. So once we can identify a ketose and an aldose, well, now we're going to start naming these aldoses and these ketoses, right? So how we name them is that because they're an aldehyde, this OSE here, OSE represents what we're going to call a sugar, right? Anything that ends in OSE is a sugar, right? You guys have heard of glucose, right? Glucose is a sugar. Lactose is a sugar, right? Uh, galactose, maltose, ribose, those are all sugars because they end in OSE. So we're going to use this OSE in the name, right? So if we have, you know what, we can use this one here. So this one here has 1, 2, 3 carbons, and we're going to use this Greek prefix, mono, di, tri, tetra, penta, right? We're going to use those there. So here, because there's 3 carbons here, the prefix on this is going to be tri. I know that it's a sugar, so it's going to end in ose. So it is a triose sugar, but we're not quite finished. This is an aldehyde functional group. So we're actually going to use part of this aldose name to name it, and this becomes aldo tri because there's 3 different carbons on there, and OSE because it's a sugar. So this becomes aldo triose. We count up the carbons, 1, 2, 3, 4, 5, 6 carbons. Aldehyde functional group. This is aldo, and because it's 6 carbons, we're going to use hexose. Aldo hexose. Let's try. All right, so let's number the carbons. 1, 2, 3, 4, 5. All right. So 5 carbons, pentose, but it does have an aldehyde functional group. That CHO is an aldehyde functional group. It's the same as if I were to do this. CHO. CHO. So 5 carbons here. It's an aldehyde functional group. So I'm going to use aldo from aldose and pentose. So here's my aldehyde functional group, 5 carbons, and then OSE because it's a sugar. So ketoses are named very similar. So if we had a ketone functional group, instead of saying aldo, we would put keto. Right? So we're still using the triose, tetrose, pentose, hexose, but we're going to use keto in front of it because we have this ketone functional group right here. All right, so 4 carbons. So I know it's a ketone, so I'm going to start it off with keto, 4 carbons, tetrose, not tetraose, but tetros. 1, 2, 3, 4, 5, 6, because we have a Fischer projection here. So don't forget that this is a carbonyl, and don't forget that that is a carbon. So there are 6 carbons here. So I'm going to begin it with keto because it's a ketone functional group. 6 carbons, hexose. So keto hexose. Number the carbons: 1, 2, 3, 4, 5. Keto because of the ketone functional group, 5 carbons, and it's keto pentose. So that's how we're going to generically name these sugars here. Uh, they do have some specific names, but we'll get into that in just a little bit. So all of these sugars, right? These sugars here have what we call isomers, right? Because if we're looking at this here, and if we're looking at this here, we know that those are going away. I'm sorry, nope. Those are going not away. Those are going towards you. They're on a horizontal line. So this is also going towards you. So if we got a mirror image of this, is that those would be facing the opposite direction. So we do get isomers from these structures. So what we're going to talk about now is we're going to talk about some more isomers, what we're going to call D and L isomers. And Dnl isomers are going to be identified by looking, so look at the second to last carbon. The second to last carbon. Don't look at the last carbon. We look at the second to last carbon. And what you're going to look for is you're going to look for this hydroxy group. If the hydroxy group on the second to last carbon, 1, 2, 3. Here's my second to last carbon. If it's on the left-hand side, it's considered the L isomer. If it's on the right-hand side, right, D for dextero, or derecho if you speak Spanish, right, is that here, this is going to be D. So if it's on the left, it's an L isomer. If it's on the right, it's the D isomer. But you always look at the second to last carbon. As far as glyceraldehyde is concerned, you don't, we're going to be looking at glycerol later today, and we'll talk more about that structure. So the second to last carbon. So you don't necessarily need to memorize. You don't need to memorize ribulose, sorbose, and idose. But what we should be able to do is we should be able to identify whether it's a D or L isomer. So we go to the second to last carbon. The second to last carbon, the second to last carbon. It's on the right. This is D-ribulose. It's on the left, L-sorbose. It's on the right, D-idose. So we're always just looking to see if it's on the left-hand side or it's on the right-hand side, right? So not difficult to discern whether we have D or L isomers in our structures. Let's take a look at one up here. Let's go backtrack a little bit. So if we take a look at this one here, well, is this D or is this L? Well, I want to make sure that you look at this. So this, and actually, you know what? Let's look at this is definitely the D isomer. Let me erase some of this stuff up here. And if we take a look at the next one, well, is it D or is it L? And again, this is the D isomer. Don't let these structures fool you. The rule is not look at the last carbon, look at the second to last carbon. This is the last carbon. This is the second to last carbon. This is the last carbon. This is the second to last carbon. And that's where I'm going to look for my D or L isomer. That this is D, this is D, because I'm looking at the second to last carbon. I'm not looking at the last carbon. Right? It's always the second to last carbon when we're looking at these structures. All right. So we know about stereoisomers and chirality, and we've talked about enantiomers, and now we have Dnl isomers, and now we're going to have some other isomers. So these other isomers, these structures here, all of these sugars can close up and form ring structures. So these can form ring structures, and we're going to talk what we call alpha and beta isomers, right, or anomers. So these ring structures are what we're going to call Haworth structures. So before we look any more at this, I have a slide in here. There we go. So let me draw this here. This is so this is glucose here. So I'm going to number these carbons here. 1, 2, 3, 4, 5, 6. and I'm going to number them here as well. So these fold up into rings, and we can look at it: 1, carbon number 2, 3, 4, 5, and 6. And when it closes up, notice the oxygen here. When it closes up, that double bond is removed, and it closes up into a structure that we see just down below here. And I'm going to number them again. So 1, 2, 3, 4, 5, 6. And we notice that carbon number 6 is on the outside of this ring. That this structure, this Fischer projection, and again, this is a Fischer projection, this is a Haworth structure. So our Fischer projection, when we make a ring structure, carbon number 5, and then there's an oxygen here. Carbon number 5, and then there's an oxygen there. So this closes up from carbon number 1 to carbon number 5. Carbon number 1 to carbon number 5, right? And then they're bonded through this oxygen that sits on carbon number 5. When it closes, though, see this? There's an arrow right here. So this arrow, we don't know the direction that this carbonyl is going to be facing when it closes up. So if it closes up, this hydroxy group could be pointing downward. If this carbonyl is facing up, that hydroxy group is going to be now in a different direction. And this is what entails our alpha and beta anomers, these isomers here. So here, we look at the hydroxy group. We look at the hydroxy group. If the hydroxy group is pointing down, we get the alpha anomer. If the hydroxy group is pointing up, we get the beta anomer. You do have to know, you are going to have to know the Fischer projection and the Haworth structure for glucose. So this is glucose here. I'll help you identify glucose. There's a pattern that I use. Every time I draw glucose, I draw it out the same exact way every single time, and it's just now out of habit. So I know glucose has 6 carbons because I've memorized that. So you memorize that too. Glucose, 6 carbons. So I know that glucose has an aldehyde functional group, and I know that it has 6 carbons. So without drawing the rest of my carbons, there's my carbon number 1, and there's carbon number 6. Carbon number 1, carbon number 6, and I'm just going to put the rest of them in here. So 2, 3, 4, 5. So now I have 6 carbons here. And then it's a pattern here. I start from carbon number 2, and I go right, left, right, right. There we go. Right, left, right, right. And I've just drawn second to last carbon. This is D-glucose. If I wanted L-glucose, I'd flip that last one around to the other side. Let me fill these up with hydrogens before I forget. All right. But that's a pattern that I've used in order to draw glucose out. Now, when you're looking at these Haworth projections, or these Haworth structures, not projections, these Haworth structures, I'm only looking at carbons number 2, carbon number 3, and carbon number 4. And there's a pattern with these that I memorize as well. I don't look at any other carbons. I strictly look at carbons number 2, 3, and 4. Down, up, down. And that's the hydroxy group here. And we notice it here, down, up, down. And I know that I have glucose looking at these structures. And then we can tell whether it's alpha or beta. So one thing that you also need to know here is that this Fischer projection can only tell D or L. You can't tell alpha and beta from a Fischer projection, and you can't tell D or L from a Haworth structure. You need both in order to determine both of them. So what I mean by that is if we were to look at this structure here, let's take a look at idose here. Let's take a look at idose. Well, we know it's a D, but is this alpha or is this beta? Well, I can't tell. I have no idea because I don't have the Haworth structure. The only thing I can get from here is whether it's D or L. So when we're looking at these other sugars here, well, is this D or L? Well, I have no idea if it's D or L. All I can tell if it's alpha or beta because this is a Haworth structure. All right, so looking at these here, so let's look at this one here. Well, is this alpha or is this beta? Pointing down, that is alpha. Hydroxy downward, alpha. Hydroxy up, that's beta. So we can definitely tell alpha and beta from these structures here. And if we talk about what I just mentioned a few minutes ago here, and this pattern, carbons number 2, 3, and 4 that goes down, up, down, well, which one of these Haworth structures is glucose? Up, up, down. Yeah, that's not glucose. Down, up, up. Yeah, that's not glucose. Down, up, down. That is glucose. Because I've looked at carbons number 2, 3, and 4, and I found that pattern of down, up, down. All right. Another type of structure. So these are all made with aldoses. So aldoses form these 6-membered rings here. So now let's look at ketosis, right? Here is my ketone. Here's my ketone functional group, right? So I know that this is a ketone. And we see that it makes a slightly different ring here. And notice these numbers here, carbon number 1, 2, 3, 4, 5, and carbon number 6. Carbons number 1, 2, 3, 4, 5, and carbons number 6. And again, carbon number 6 is out of the ring, but also carbon number 1 is also on the outside of that ring. In order to determine alpha and beta, well, we take a look at the hydroxy group. We're always looking at the hydroxy group. And again, we still look at this hydroxy group. So hydroxy group, not the CH2OH, right? And then we're not looking at this here. We're looking here at carbon number 2. Carbon number 2 is where this carbonyl was at. We go back to the structure up here. Carbon number 1, this is where our carbonyl was at. Our carbonyl was located here on carbon number 1. And we look at that hydroxy group. Our carbonyl is on carbon number 2, and we look at that hydroxy group. And this is how we can determine between alpha and beta, is by still looking at that hydroxy group. And other structures that you do need to be aware of is, yes, you do need to know the Fischer projection for fructose and the Howard structure of fructose. Just like you need to know for the exam, you need to know the structure of glucose, Howard structure, and Fischer projection for both glucose and fructose. The pattern for fructose, instead of looking at carbons number 2, 3, and 4, we're simply just going to look at carbons 3 and 4. And we see the pattern is up, and we see the pattern is down. So pattern up, pattern down, and then carbons number 3, 4, and 5. So we go left, right, right, as far as the Fischer projection goes for fructose. All right, so let's see, how much more do we have here? Nope, let's go ahead and finish this off, and then we'll take a break because we're almost actually done with Unit 10. Unit 10 is not very long, so let's keep going here. All right, so when we talk about oxidizing, ketoses don't oxidize very easily. It does take a bit of work. So, you know what? Give me 1 second here. All right. So, what happens is that ketosis, if we go back to organic chemistry and we take a look at oxidation, so we take a primary alcohol, we oxidize that, and we get an aldehyde, and we oxidize that again, and we get carboxylic acid. And then if we take a secondary alcohol and we oxidize that, we get a ketone. And if we try and oxidize that, we get no reaction. So we notice that ketones, and let me write ketone. Ketones do not oxidize. So that's why we have ketoses don't easily oxidize. So even though that there is a ketone functional group, a ketose will oxidize. What happens is they undergo something we call isomerization. Isomer is in there, isomerization. So what happens is that this ketose here, which is named fructose, will undergo isomerization. It will rearrange itself into an aldose. And aldehydes can be oxidized. So aldoses and ketoses, because they can rearrange themselves into aldoses. Ketoses and aldoses both oxidize. So I'm going to skip this section real quick. We'll go back to it. They will all oxidize. So here we have this reaction here. So we're gonna go back to some general chemistry real quick. We're gonna take a look at. Let's take a look at zinc plus. We'll take a look at copper chloride, and we're gonna get zinc chloride plus we're gonna get some copper. That's a solid. This is solid aqueous. All right. So here, just kind of a review of general chemistry here. Oxidation number for zinc is 0. For chlorine, it's -1, and for copper, it's +2. And over here, we're going to get +2 for zinc. Chlorine is still -1, and now copper is 0. So if we take a look at what's oxidized and what's reduced, zinc goes from 0 to zinc +2. And copper goes from +2 to copper 0. So the copper was reduced and the zinc was oxidized. The copper was reduced and the zinc is oxidized. But let's look at the zinc real quick. The zinc was oxidized, right? The copper was reduced. I keep repeating this because it's really important to kind of understand this for what's going on in the reaction. If the copper was reduced, what reduced the copper? The copper was reduced, but what was it that reduced it? The zinc reduced the copper. The copper oxidized the zinc. The zinc was oxidized, but it's the copper that did it. The copper was reduced, but it's the zinc that reduced it. So the zinc was oxidized, but the zinc is also going to be known as the reducing agent. And if the copper was reduced, the copper was the oxidizing agent. But biochemists are a little funny. They don't like to use reducing agent. So this is where we're going to get this term, reducing sugar. Reducing sugar because it's going to reduce, just like zinc reduce the copper, sugars can reduce this copper. So we go from copper +2 to copper +1. And it's the sugar that reduced it. So all sugars, I'm going to say all monosaccharides. If we want to know what a monosaccharide is, this is a monosaccharide. It's a sugar that's all by itself. All of these are examples of monosaccharides. We're looking, all these are monosaccharides. They're all sugars that are by themselves. All of these sugars are by themselves. They're all monosaccharides. Whether they're ketose or aldose, they're monosaccharides. And all monosaccharides are reducing sugars. Now, as far as this disaccharide goes, this is a disaccharide where we have two sugars that are bonded through this oxygen bridge. Di meaning two, right? So all monosaccharides and all common disaccharides, except for sucrose, which we'll see, are reducing sugar. So sucrose is not a reducing sugar, even though it's a disaccharide. So all monosaccharides, whether they're ketose or aldose, are reducing sugars, and most common disaccharides are also reducing sugars. All right. So, I mean, I put it in red here. It's in bold for a reason. So I want to make sure that we understand that statement there, right? So this is what we're going to use. And you guys are going to go over Benedict's reagent. You guys are going to go over this reaction in the lab for lab 10 or 11. I think it might be 11 that you guys will see this. I think it'll be the final lab of the semester. All right. So now these, what we're going to call saccharides. So carbohydrates are also called saccharides, right? They're just sugars, right? So these monosaccharides, so we have monosaccharides, disaccharides, oligosaccharides, and polysaccharides. So we've gone over monosaccharides. Monosaccharides are just these small one carbohydrate units, right? Can't be broken down into anything further. Is that this one unit here is going to be considered a monosaccharide. And when we have two of them bonded together, it's a disaccharide. But that's where we stop. We're not going to go trisaccharide, tetrasaccharide, it just 1, 2, and anything from 3 to 10 is going to be considered an oligosaccharide. So here we have 1, 2, 3, 4 of these saccharide units, and this is going to be considered an oligosaccharide. So whether it has 4, 7, 8, 9, 10, they're all under this term oligosaccharide. Then when we get more than 10, we consider that a polysaccharide. So this here, this is just kind of a zoomed in portion of what we see here. And so this is our polysaccharide. So whether it contains 11 saccharide units or whether it contains 500,000, they're both going to be considered polysaccharides. So let's go back and talk about disaccharides. So I know this looks very complex, but we're going to kind of break this down. You don't have to memorize the reaction here. What you do need to know from this is that glucose and another glucose, right? Because here we see the plus sign. So if we take two glucose units, that's going to make maltose. This is maltose. You don't have to memorize that structure. You only need to know that glucose plus glucose make maltose, right? Glucose plus glucose make maltose. We'll go over something here. I'm going to go over the rest of these disaccharides, and we're going to come back and we're going to revisit this glycosidic bond. So other disaccharides here. Here we see another one. It's bonded slightly different. This is sucrose. So again, you don't have to memorize the structure of sucrose. What you do have to know is that you need to know that glucose plus fructose make, glucose, yes, make sucrose. Right. So that's what you need to know there. And again, we'll visit this bond in just a second here. Let's go over another sugar. This one is lactose. And galactose plus glucose make lactose. Right, and that's the information that we need to know there. All right, so now let's take a look at this. Let's kind of dissect these reactions because there is something about these that we do need to identify. So this here, I'm going to circle it. This oxygen bridge here has a specific name, and these oxygen bridges can be bonded differently. It does not necessarily have to be, it's not necessarily required to bond to monosaccharides between carbons number 1 and number 4. But here we do see that. So that's how we get this name. This alpha, because if I take a look at carbon number 1 over here, it's in the alpha position. It's the alpha anomer. So this is, let's take a look at this. Let's back up here. Before we split this up, and actually let me get rid of these colors because I don't want you to match these up here. I'm going to circle this in red because I'm also going to circle this in red. So let's match those up. So this alpha here, alpha, because before the sugar was bonded together, this sugar was in the alpha position. So alpha, and it's bonded between carbons number 1 and carbon number 4. Alpha 1,4 glycosidic bond. Now let's take a look at it differently now. So here, I'm going to redraw the one on the left. And I'm going to draw it like this. And notice that this hydroxy group is in the beta position. So we notice that this beta position causes the bond to look much different. We see how that O is pointing up, and in the previous one, we see that O pointing down because of this hydroxy group and its placement. So because this hydroxy group is pointing up is why this is bonded differently, but because this is in the beta position, let's number these carbons. 1, I'm going to circle this, that this is going to be labeled as beta. It's bonded at carbon number 1 and bonded again at carbon number 4. And then I'm just going to add the term that we need to memorize, glycosidic bond. So this is a beta 1,4 glycosidic bond. I don't really even have to draw the rest of it. The only thing that we have to do here, let's see, how about, the rest of it really is irrelevant here. All right. when I bond these two, let's make a disaccharide from this. Um, all right, so the rest of it is really just irrelevant here. What I'm going to be looking at is I'm going to number these 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, what I'm going to look at is I want to know the direction of this oxygen. And the direction is kind of pointing up, which tells me that it is going to be beta. And I'm looking at this particular bond, this oxygen bridge here, and that oxygen's kind of pointing upward. And it's bonded between carbons number 1 and carbons number 3. So this is a beta 1,3. And then the term we memorize, glycosidic bond. Let's look at one more. Actually, what is it on here? Let me see if it's even on here. Nope, I don't have an image of it, but we do need to know what it looks like. Let's see. All right, so we get a structure. How about? All right, so here I'm going to number these carbons. And I'm going to circle the bond. Here's this oxygen bridge here. So I've circled that oxygen bridge, and we can see that this oxygen is kind of pointing downward, which means that that's going to be alpha. So we have this alpha, and then I take a look at the carbons, carbons number 6, carbons number 1. This is an alpha 1,6, and the term we memorize, glycosidic bond. So that is an
Alex,
alpha 1,6. Yes.
Professor Alex, you start uh, counting the carbons or naming the carbon like the 1, 2. Where do you start? How would I?
Always begin the for this particular structure. We're looking at two different ones. Let me backtrack a little bit here. So we see two different types of structures here. So if we see a structure that has 6 sides, right?
Yes.
Carbon number 1 is always going to be to the right of that oxygen.
Okay.
That's carbon number 1. If the sugar has 5 sides, like this one, that is carbon, that particular carbon right there, is going to be carbon number 2. Carbon number 1 sits outside of that.
Okay.
And we always count in this clockwise direction after that, right?
Okay.
So again, 6-membered ring. Here's carbon number 1. It's to the right of that oxygen that we see here.
Okay.
For a structure like this, let me see if we have let me see something fresh that's not actually written down. Let's take a look at this one, right? So it's already labeled here, but it's okay. Let's kind of clean this up a little bit, right? 6-membered ring, carbon number 1. Five-sided ring. Here's 5 sides, and that's going to be carbon number 2 because carbon number 1 is outside of that structure.
Okay.
Carbon's number 1. And carbon's number 6. Carbon number 1 and carbon number 6 are not part of the ring structure when there's only 5 sides. Does that help?
Yes.
Okay.
Thank you.
Mm-hmm. All right. So I think finally, let's take a look at this one here. So this is sucrose here. And sucrose, notice that it's alpha and it's beta. Is that these carbons right here. So this is what we're going to call, this is our anomer right here. This is our anomer, and this is our anomer. And both anomers are involved in this oxygen bridge. So much different than the structure like this, where here's carbon number 1, and that's my anomer. Here's carbon number, again, carbon number 1, and there's my other anomer, but this anomer is not involved in this bond. This bond here only involves one anomer. Is that this anomer over here is not part of this oxygen bridge, this glycosidic bond. So this glycosidic bond only contains one anomer, and that anomer is always the carbon to the right of that oxygen, right? That's where our anomer is. And here, well, here's my anomer. Let me erase some of this stuff here because now it's quite messy. All right. So here, if this is my anomer, and this is my anomer, carbons 1 and carbon 2, look at this. Look at this bond here. This bond involves this anomer, and it also involves this anomer. So both anomers are involved in that bond. So alpha, beta, and we use both of them in that glycosidic bond, bonded from carbon number 1 and bonded to carbon number 2. Right. So because both of these anomers are involved, this is why sucrose is not a reducing sugar, is because both of these anomers are involved in that glycosidic bond. Sucrose is not a reducing sugar. All right, so just a few more minutes, then we'll take a break here. So all of these monosaccharides can form what we call polymers, right? And they're just identical repeating units. Right. So this is what we call them. This is a monomer here. Let me circle it. So this is a monomer, this is a monomer, and they're all exactly the same here. And that's what makes up these what we call polymers. It's just these repeating units. So we're going to talk about starch, glycogen, and cellulose. So starch, right, is this primary storage in plants, right? Primary storage in plants for these glucose units. Now, uh, amylose is one of the smaller ones here. So all of these monomers here are glucose. And they're all bonded by this alpha 1,4 glycosidic bond, glycosidic linkage. It's the same thing, right? But they're all bonded the same way. And again, they're all glucose. Uh, these can start getting branches, and we've seen branches in organic chemistry. So amylose does not have any branch points. Amylopectin, though, does have some branching. And again, these are all still glucose units. All of those are still glucose. And then here we see this branch here, right? Everything here is bonded alpha 1,4, except for this branch. All the branches occur at alpha 1,6. So everything else is bonded alpha 1,4, except for the branches that occur. The branches occur at alpha 1,6. And then we have, this is what we're going to call highly branched, right? Glycogen is a highly branched unit. Still all consisting, again, all of these monomers are glucose. They're all bonded by alpha 1,4 glycosidic bonds. But this one's highly branched, and all of these branches, again, all of the branches here occur at alpha 1,6. Right, so alpha 1,6. So we see all these branches here. Here's another branch, right? Here's another branch. So all of this branching occurs, and this is what's going to be glycogen. And this is the glucose storage unit for animals. So glycogen is the storage unit for animals. Starch is the glucose storage, is the way that plants store glucose is by starch, and we use it in. For us, it's glycogen. Not to be confused with cellulose. Cellulose is not how plants store glucose, right? Cellulose is used for structure, right? Cell walls, plant walls, right? So if you see a blade of grass, right, that's what's helping it stand up straight, is that it's got cellulose there, and it's used for structure. But cellulose is bonded by beta 1,4. Right? So here we see starch, and the starch is bonded alpha 1,4. We get this nice straight line here. And then beta 1,4, we kind of see the stepwise structure, right? Because we kind of see it going off upwardly, which is going to signify that this is a beta 1,4, and this is going to be your cellulose chain, right? This is also referred to as fiber. Like we can't break down fiber. We don't have the enzyme. We don't have the right enzyme that'll break that particular uh, bond up, but we do have, right? We do have enzymes that'll break the alpha 1,4, but not necessarily the beta 1,4. So uh, fiber, will pass through us. It's kind of like, you guys, I'm sure somebody in here has eaten too much corn, right? Or if you've changed a baby diapers, like I changed my grandbaby's diapers, and trust me, I know when they've eaten corn, right? Goes in as corn, comes out as corn because they didn't didn't chew it up right? All that fiber in that corn, that cell wall there, is still put together. All right, so this will cover Unit 10. Unit 10, I'm actually going to stop the recording, and then I'll start another recording for Unit 11. All right, so we've covered Unit 10. This is now going to be on Unit 11. So Unit 11, we're going to stop once we get to proteins. So this is Unit 11 consists of lipids and proteins, and we're just going to cover the lipids portion here. Um, so lipids are biochemical compounds, right? These biochemical compounds contain carbon, hydrogen, oxygen, but they're not like carbohydrates. Like carbohydrates, they saw the same thing. Carbohydrates had carbon, oxygen, hydrogen, but the structure is really a lot different than what we've seen as carbohydrates go. Right? So carbohydrates, lipids, carbohydrates are soluble in water because of all of the hydroxy groups. Let me draw a carve out real quick. Because of all of the oxygens that are in carbohydrates, those are soluble in water. So you can put sugar into water and it dissolves just fine, right? Uh, glucose, lactose, you can put all of those in water and they will dissolve in water. But lipids are insoluble in water. Lipids are a lot larger and they contain a lot less oxygen. That majority of lipids are going to are structured from carbon and hydrogen, and then involve a little bit of oxygen. Right? So because they're insoluble in water, most, not all of it, but most of the lipid is what we're going to consider hydrophobic because of this carbon hydrogen bond. So we've talked about this bond before back in general chemistry. We took a look at this bond and uh, we take a look at this bond here. So if we just kind of remind ourselves what happened here is that this is partially negative, this is partially positive, and we have this polarity here, this pole here, and that's what helps this dissolve in water. But here we don't have that. There's no partially positive, partially negative, and if we remember anything, that this is a non-polar, a non-polar covalent bond, right? Non-polar. And the other non-polar bond is this, that carbon and hydrogen are also non-polar. And because it's non-polar, water with its partially positive, partially negative end has no attraction to anything that's nonpolar. In order for water to form hydrogen bonds, has to be attracted to something that's partially negative or partially positive. But if there's no partially negative or partially positive, and if it's nonpolar, then the water's not going to be attracted to that. And again, that's what happens with these carbon hydrogen bonds here. So the two major categories of lipids that we're going to cover are what we're going to call fatty acid lipids and non-fatty acid lipids. So as far as fatty acid lipids, we'll cover fats and oils, waxes, and then phospholipids. And our only non-fatty acids that we're going to talk about in this unit is going to be steroids. There are others, but as far as this section goes, we're only going to talk about steroids here. Excuse me. All right. So lipids are long-chain carboxylic acids, right? That's where we get this term fatty acids, right? Fats, nope, is fats, right? Fatty acid because they contain this carboxylic functional group, right? This carboxylic acid functional group. And most of them range in anywhere from 10 to 20 carbons long. And we have a couple different types. We have what we call saturated fatty acids and then unsaturated fatty acids. As far as unsaturated fatty acids, there's only two kinds of unsaturated fatty acids. Either if it has one double bond in the chain, it's monounsaturated. And if it has two, we don't go disaturated, triunsaturated. It's just polyunsaturated at that point. If it has more than one, it's just polyunsaturated. So let's take a look at some examples here. So when we talk about saturated fatty acids, we're looking at all of these hydrogens here, this whole carbon chain here, and we see there's no double bond. There's nowhere else on this molecule that I'm going to fit any more hydrogen. Uh, Nowhere else, because carbon can only have 4 bonds, and this is saturated. So when we say it's saturated with hydrogens. Then if we take a look at the example down below that, we see this is going to be what we call polyunsaturated because I have more than one. If there's only one, this would be monounsaturated, but this is poly because it's two. And this is an unsaturated fatty acid because it is possible through hydrogenation to break that double bond and add some more hydrogen there. So this isn't fully saturated with hydrogens. So here's our examples of what we consider saturated and unsaturated fatty acids. All again in these fatty acids, and there it is, carboxylic acid functional group. So this is a functional group you definitely want to know is this carboxylic acid functional group here. um, you know what? And I think not with all of my notes. I'm going to put a blank uh, I'm going to put a blank PowerPoint, or I'll put a blank lecture slide up, not with all of my notes, but I will put a blank, you know, maybe I'll just do it with the notes. Yep, you know what? Whatever I have here, I'm just going to upload it for you guys because there's in units 10, 11, and 12, there's a lot of images. So don't feel overwhelmed that you're not writing everything down. Is that I will take this presentation here along and I'll upload that into Canvas for you guys because there really is just a lot of drawings that are going on here and I don't want you guys to feel like you don't have all the information you guys need because I can't draw all these out myself. I'd be here for 5 hours giving the lectures if I had to draw all this out. So I will upload these for you guys with all the notes included. All right. So here, right? So just again, a couple of examples. Now, when we talk about these unsaturated fatty acids, don't forget these terms that we've learned in organic chemistry, right? We have trans and cis fatty acids. So trans and cis fatty acids, you can see the shape of them are much different here. So fatty acids, unsaturated fatty acids, even though they're unsaturated, trans fatty acids, trans fatty acids can still stack together very nicely. And I know the double bonds are in a different place. They don't necessarily all have to be in the same place. But we can see that they stack together very nicely. So trans fatty acids are still pretty dense, but cis fatty acids, you'll notice cis fatty acids are liquid at room temperature, right? It's not like lard, right? Like, you know, we have saturated fatty acids like lard. We have some trans fatty acids um, that are still solids at room temperature. And then we have cis fatty acids, and you'll know a cis fatty acid because they're going to be liquid at room temperature. If I try and draw cis fatty acids, let me draw a couple here, and you'll see that they don't stack together very well. right? You can already kind of see that they're not stacking together very well. I'd have to maybe draw another one over here in like kind of like this direction. And they just don't stack together very nicely. It's not like these like these here. These are trans fatty acids, and they do stack very nice. It's one right on top of each other, just like a saturated fatty acid would stack together very nicely, right? Just put one, just stack one right on top of each other, you know. But these cis fatty acids, uh, like this, you can just tell by looking at it that they're just not going to stack together very well, and this is why they're liquid at room temperature. You guys are going to have this in your book. Don't get overwhelmed by this. You don't have to memorize all these names and the formulas, right? Don't go out and do that. Don't spend all week trying to memorize the formula and the names. You're not going to have to do that. What we do need to understand is we do need to understand this information here, right? And we put this together like this 18.3 here, or even 18. Let's do it. Yeah, 18.3. All that means is that there's 18 carbons and that there's 3 double bonds in there somewhere, right? So I could write 16.2, right? Which means that there's going to be 16 carbons and there's going to be 2 double bonds in there somewhere. Um, so if we take a look at this here, so that's what that means there. I want to take one here and I want to draw it out because your homework is going to ask you to do something very similar to this. Um, so what I'm going to do here is I'm going to take this very last one here. I'll move that information over here, 16.2. This is for the number of double bonds, and this is for the number. So I'm going to redraw this. So this linolenic acid here, I'm just going to flip this around, and I'm going to do this. All right. So I've just kind of written it in reverse. Right? And now I'm actually going to draw the structure. So when you see this CO2H, that's your carboxylic acid functional group. There it is, CO2H. So CO2H there. So I'm going to draw that out. And then if I follow it, so I've taken care of this. Let me take care of this. I have 6 CH2s. 1, 2, 3, 4, 5, 6. And you know what? How about we do this? I think I'll stick with just condensed structure formula. I don't think we'll go with line formula. So I'm going to go CH2. There's 6 of them. And then I have CH2, CH, CH, and there's 3 of them. And then I have CH2, CH3. So I've kind of written this out in a structure that's a lot more recognizable than just simply this. Because we are going to be working with these fatty acids, you do need to be able to take this and turn it into something like this, right? So first I have to reverse it, and then I actually have to put that carboxylic acid functional group on it, because we're going to be doing reactions with this, right? We're going to be doing reactions with it. We've talked about glyceraldehyde. This is glycerol, right? So this is glycerol. There's a couple different ways you're going to see this. You can see this as a CH2OH. Get better. All right, so again, it's the same thing, that this is also glycerol. If I draw it in line formula, it'll look like this. All right, but those are examples of glycerol there. So here we recognize this portion here, because we're going to be making something that we call a triglyceride. Triglycerides involve glycerol, plus they involve some fatty acid, right? So it's glycerol plus some fatty acid, and that's going to make what we call that's what we're going to consider a fatty acid. I'm sorry, a triglyceride. All right. So triglycerides, we've seen this reaction before. This reaction is not a new reaction in order to make a triglyceride. Triglycerides are made of 3 ester bonds. So in order to make an ester, we need an alcohol, I need an alcohol, plus I need a carboxylic acid, I need some acid, all right, so here it is. So I take an alcohol, plus I take a carboxylic acid, and I get this ester. Here, and it just so happens that if we take a look at glycerol, glycerol contains 1, 2, 3 alcohol groups. So here is my alcohol, and here is my carboxylic acid. Alcohol plus carboxylic acid, and I get this ester. And our ester is, right? If we look at it, it's right here. And that's the same thing that we have up here, right? So alcohol plus carboxylic acid, and I get my ester. But because we're using glycerol and there's 3 alcohol groups on it, I have 3 ester bonds. And this whole thing right here, this large lipid here, is what we call a triglyceride. So we get triglyceride plus we get some water. But this is just an esterification reaction, similar to what we saw in organic chemistry. We just do it threefold because we have three alcohol groups on that glycerol. Right? So again, here it is again, right? Here's my ester, here's my ester. So triglycerides don't necessarily have to have the same fatty acid. You can see that this particular one has three different fatty acids. I have a saturated fatty acid, then I have a mono unsaturated fatty acid, and then I have a poly unsaturated fatty acid. So using these triglycerides is how we make soap. So it actually undergoes this reaction that we call saponification. Is that triglycerides are broken down. We know how to make a triglyceride, right? Glycerol plus fatty acid, we get triglyceride. Right. Well, we can also break this down because we have gone over, this is another reaction that we've already gone over as well. So here, that's how, this is esterification. Well, if we reverse this, well, not actually reverse it. If I take this carboxylic acid, I'm sorry, this ester here, if I take this ester and I add a base to it, this is not an unfamiliar reaction. Is that this will give me my alcohol. So I get my, what? 1, 2, 3, 4, 1, 2. So here I get my alcohol plus I get this. Does this look familiar? I get my carboxylate. Right? And this is what we call base hydrolysis. So let me write that better. Base hydrolysis. So we take an ester, add a base, we get alcohol plus a carboxylate, right? Carboxylate salt. So, but this time, instead of calling it base hydrolysis, in biochemistry, it's called saponification, right? But you do need a strong base, not a weak base, strong base, right? We know our strong bases, right? Calcium hydroxide, sodium hydroxide, potassium hydroxide, those are our strong bases. So we're going to take a strong base, we're going to get what we call glycerol, which is our alcohol, and we're going to get soap, which is our carboxylate salt. Right, so we get glycerol, which is the alcohol, because here this fat or oil, this is going to be our triglyceride. This is our ester. So here it is, saponification. And we're just going to take, I can't really cover, I wonder if I can cover this up a little bit. No, it'll be too confusing. All right. So here, we need to recognize our triglyceride here. And our triglyceride has these ester bonds here, right? So what we're going to do is we're going to break each one of those ester bonds. We're going to break it off right here, break it off right here, break it off right here. And when we do that, well, we're going to split this up into Na plus O minus, and we're going to get some H plus. Well, if we remember anything about base hydrolysis, let's go back to base hydrolysis. I'm going to get an alcohol plus a carboxylate salt. This is where we get our alcohol, our glycerol. Glycerol ends in OL. It's our alcohol. So we're going to get glycerol back. And then we're going to add this Na plus O to here. Let me color coordinate this a little bit. That way we can maybe see it a little better. Or actually remember. So I'm going to write NaO in blue. So we're going to get Na plus and O minus. And we're going to bond it to these here. This in blue. Right? So anything I have circled in blue, that's how we bond it together. Right? We bond it over how we see the stuff in blue. The stuff in red over here, right? So we get our alcohol back. So this is just kind of how we match things up. But this is what's going to be considered our soap, right? Is the long carboxylate salt on there. You can kind of use this as a template, I believe. You're going to have some homework assignments pretty similar to this. So you guys are going to have to probably go in your, let's see here. Actually do one. Let me pull up the table. All right, so on your table on 11-12 for those of you that have your books. All right, so we're going to says, let's see. We're going to write out a balanced equation similar to what we did, or similar to what we saw up here. So a particular glyceride contains myristic acid, palmitic acid, and oleic acid. Well, the first thing I'm going to draw is I'm going to draw my glycerol backbone. CH2O, CHO, CH2O. And that's the triglyceride backbone. And it's shown everywhere here, right? So here's the backbone to this glyceraldehyde, or this triglyceride, CH2O. So that's all I've done here. And now I'm going to add each one of these acids, fatty acids, to that glyceraldehyde or that glycerol backbone. So the first one says myristic acid. That's CO2H. If you're looking on 11-12, that CO2H is this. Right? So I've added the carboxylic, I've added my carbonyl, and now I'm going to go 12 CH2s, CH2, and there's 12 of them, and then I have a CH3. And I'm going to go to palmitic acid. I'm going to put this information in here, and then I have CH2, 14 of them, CH2, 14 of them, and then CH3. And oleic acid, carbonyl here, and I'm going to write it backwards. So I have CH2, 7 of them. Oh, and I have CH, double bonded to another carbon hydrogen, CH2, 7, and I have CH3. So this is the glyceride. So that glyceride is right here. Now it's telling me that I'm going to add some sodium hydroxide to that. So I've added my sodium hydroxide. Uh, for base hydrolysis, for saponification, 1 sodium for 1 salt. 3, because I had to break that bond 3 times. So I need 3 sodium hydroxides because I'm going to break this bond here between the carbonyl and the oxygen, I'm going to break that 3 times. So I need 3 moles of that base. So let's see what we're going to get here. Um, we're going to break it off here. So this is how we're going to split it off. We're going to split it off in that OH and this here. So we need alcohol first. So the alcohol is going to be our glycerol, CH2OH. So we've gotten our glycerol back. That's our alcohol. Now we need to get the rest of it. So we're going to add, I'm just going to draw this up here. So let me draw this up here. CH2, there's 12 of them. I have CH3. I'm going to have CH2. There's 14 of them. There's 7 of them. CH double bonded. There's my double bond. CH2, 7, 3. And now I'm going to add this NaO to it. A lot of work goes into this reactions. You have to do these reactions for the homework, but you're not going to make these reactions on the exam, right? So just kind of understand that. I'm not going to have you draw these, so but you have to understand the reaction. You have to know what's going on in the reaction, but you don't necessarily have to do this entire reaction, but you do have to understand what's going on in there. So the homework's going to be really helpful as far as anything you might see on the exam, right? But there's a lot of work going on here. So, again, I'm going to post these up for you guys because this is a really lengthy reaction here. But we do get our, and this is what's going to be considered our soap here. So this is our soap. So we get glycerol plus we get some soap from this. Nope, I think we just kind of Myristic Palmitic Oleic. Yeah, we just did this one. And oh my gosh, I can't believe I had these here. I didn't even have to draw this out. So here is Myristic acid, oleic acid. This is the exact same one we just did. This is a lot cleaner than my writing. We had our 3 bases, our 3 moles of NaOH. We get glycerol. Plus we get the original, there's 1 salt there, carboxylate salt, there's another salt, and there's another salt. So this one's really a lot cleaner than what I wrote out there. So luckily, I'm glad I had this and I didn't realize it. So good. All right. Polyunsaturated and monounsaturated fatty acids can undergo hydrogenation, right? So we can turn them into fatty acids, right? We can turn them into saturated fatty acids. And however many double bonds they have is how many moles of hydrogen it's going to require. So here we see 2 double bonds here, which means that it's going to require 2 moles of H2, right? 2 moles of H2. And that's, if I got 2 moles, that's where we have 1, 2, 3, 4 here, right? That's simple math. But we are going to need 2 moles of H2 in order to go ahead and hydrogenate that. But it is just a hydrogenation reaction from organic chemistry that we've seen. So here, and maybe we should do a little review on that. So hydrogenation reaction. So let's see. So here's an alkene plus H2. I'll use some palladium. And we get this structure here, right? So that's hydrogenation reaction. So we can do that with any of our fatty acids. So if we do that here, how many moles of H2 are going to be required? Well, let's see how many double bonds that we have. I have 1 double bond here. I have 2 double bonds here, which means I have 3. So I'm going to need 3 moles of H2 because I have 3 double bonds. So let's go ahead and let's see what we're going to have for this, which means we're going to remove these double bonds here. So how many carbons are actually here? Because we have to get this right. We're not going to break this up like we did for saponification. All we're doing here is we're removing the double bonds, and that's it. So I'm going to all right. I have 7, 8, 9. 9 plus the 7 is 16, 17. So 17 carbons are in this chain, not including the carbonyl. Here I have 6, 7, 8, 9. 2 of them, 10, 11, 12. 12 plus 4, 16. 17. So again, 17 carbons here. So because I remove these double bonds, I can just simply write these as CH2 because I've removed those double bonds. So I can actually write this out as CH2. There's 17 including, I don't want my math to get too complicated. I'm doing this in my head, but from here, this is 16 carbons, 16 CH2s, and then I have just this one CH3. So from here to here, I have 16 CH2s and 1 CH3. And then I'll just rewrite this down here because nothing happened to that. C18C. So here is what the question is asking us. How many moles did we get? And after we hydrogenate that fatty acid. So I hope my counting wasn't too complex as far as getting all of those. I'm going to count them up just one more time so we can see it. Is that here, from here to here, I'm going to count 16 carbons. There's 7, 8, 9, plus these 7. That gives me 16. After we hydrogenate it and add some hydrogen there, I'm going to get 16 of these CH2s plus I have my CH3. And that's what we did over here. And how I count these is I have to see this 2 here. So here's 6, 7, 8, 9, 10, 11, 12. 12 plus 14. So this is going to give me 16 CH2s plus my CH3. And that's what we did here. So I hope that kind of clears up my counting when I'm doing those CH2s there. And oh, that's just everything we just did. All right. So I think that'll cover our our fatty acid lipids when we're talking about oils, fats and oils. So another type of fatty acid lipids are waxes. So waxes are really just boring. I'm going to be done with waxes in about 2 minutes. We're not going to name these waxes. We're not doing reactions with waxes. We're going to identify what a wax is, right? So wax is nothing more than just an ester bond, right? We take a fatty acid plus an alcohol, and we get this wax. So these waxes are here. Let me draw an ester here. I'm going to draw 2 of them here. So I think this will kind of clear things up. So this is an ester. This is a wax. You guys can see the difference, right? That this is just a small chain ester, and this over here is a wax. So waxes are just esters, but they just have really, really long, right? They just have these really long tails on here that are nonpolar. These are going to be what we consider hydrophobic, ends here. So there's no water attracted to these tails here, but that's our difference between a wax and an ester. So I would assume that you guys would know the difference between an ester, a wax, or even something like this. All right, so we do have some different structures now. So right, so this I would consider just an ester. This is going to be known as a wax, and here, well, this is just a fatty acid, right? It's a saturated fatty acid. So just different structures that you want to be familiar with. But that'll cover waxes. So we're done with waxes. And then the last portion for our fatty acid lipids are we're going to consider phospholipids. So phospholipids are very similar to a triglyceride. They have the glycerol backbone, but I only have 2 fatty acids. Here's 1, here's 2. And now all of a sudden I have this phosphate group in there, right? So I got this phosphate in there, and all of these here, this consists of a bunch of hydrogen, carbon-hydrogen bonds, which we know are non-polar. And this end is what we're going to be considering as hydrophobic. This, because of these oxygens here, and because of these oxygens here, uh, water can bond to it, and it's attracted to water. And this is what we're going to consider as hydrophilic. So these ends over here that contain all of these These carbon-hydrogen bonds are going to be considered hydrophobic, and then we have one portion of it that's going to be hydrophilic. So what happens here is we start to, this is going to be my phosphate end, and then I'm just going to draw these little tails here, and that's going to represent the fatty acid tails. Is that autonomously, these things will rearrange, just spontaneously, they'll rearrange themselves when placed in water because one end loves water and one end can't stand water, right? And they start to orient themselves. And if you've already taken biology, this is our understanding of this phospholipid bilayer. So these phospholipid bilayers here, right? This is what starts to build our cell membranes here. Is that here's our glycerol, right? We have two fatty acid tails, and we have this hydrophilic part here, and that's kind of what we see right in here, right? Here's our phosphate, and then we have all of these hydrophobic tails there. And again, this is what will start building our cell membranes. Is from this idea is that of hydrophilic, hydrophobic areas in these phospholipids here. And that brings us to steroids. So we're almost done with the lecture here. So this will bring us to steroids. Steroids is going to be our only non-fatty acid lipid that we're going to talk about. So they contain a fused ring system. Right? So it's three cyclohexane rings, and then we get this one cyclopentane ring here. But it's a non-fatty acid because there is no carboxylic acid functional group. So this is what makes it a non-fatty acid lipid. But it's still a lipid because, I mean, take a look at the number. I have 17 carbons in this structure here, right? So this ring system here is what kind of helps us identify steroids. So what makes steroids different are all the double bonds we can put on there, all the side groups we can put on there. So you'll notice that cholesterol is a steroid, and cholesterol, well, we put an alcohol group here. There's a methyl group here, another methyl group. I have a double bond over here, and I have this big alkyl group over here. And this is what makes all of our steroids different, is the number of substituted groups, the number of bonds, the number of functional groups that we can put onto different steroid ring structures, these steroid ring system here. And that's what identifies each one of these as being unique here. So you don't have to memorize the structure of cholesterol, but you do need to know that cholesterol is a steroid. So some more steroids that we have, right? Androsterone, progesterone, estradiol. We have estrone, testosterone. And we'll notice, right? Here's a ketone structure. So instead of an alkyl group here, so it's pretty similar to cholesterol, except it doesn't have that double bond. And we have a ketone structure instead of an alkyl group there. Right? Then we have, look at this, we have a phenol group here, alcohol group. So this is what makes all of our steroids different. You don't have to memorize these structures. I'm not going to take a picture of these structures and put them on to the exam, but you do have to know these names. You have to know that these are steroids, including cholesterol. Right. So you don't have to know the structure, but you do have to know the names of these particular steroids. You have to know the ring system, right? You have to see this ring system, right? So that you do have to know. And that gets us to proteins, and I think this is where we're going to stop. So this will be the end of today's lecture. We'll continue next week with the other half of 11 and get into nucleic acids.